All right, so continuing on today, we're going to talk about sort of more generic ways, since now that we have solved this giant AX equal to B problem, in some sense. We've been talking about AX equal B for a while. We're moving on. And we're going to talk about solving partial differential equations, so things that have space and time. And we're going to start off with one dimension. And here's the concept. You have position, you have time, and then you have some solution u. And so our idea is to say, what I would like to do is to think about solving something that changes in space and time in this computational way. And the way to think about doing this is you say, if I specify the initial state of the system at some time, let's call it time 0, what I want to ask is, how's this thing going to evolve forward? Right? I want to do a prediction of the future by knowing the equations of motion. Okay? So this is what people do with any kind of modeling you would have, like global circulation models. This is about how things are changing in time and space, and so you can do weather predictions, right? So you compute forward what the thing looks like, and then you say, oh, by the way, tomorrow, mostly sunny. It's probably totally untrue, but I'm going to say it. Mostly sunny tomorrow. Is that true, actually? Does anybody know what tomorrow's going to be? Or is it going to be, we get to the weekend, it's finally not raining, and then it rains tomorrow? Hate that. Okay, I'm okay with cloudy, just not rain. Okay. By the way, this is my solution in the future. Did you see how I did those lines? They're not quite parallel. They're kind of going into a point in infinity. Dang, I'm a good drawer. I know. I can draw real well. See that? See how they're like Michelangelo up here. Okay, so what do? We chop it up in space. This is what we've been doing the whole time. Okay? You chop it in space, and then you chop it in time. Here's your delta t's. Here are delta x's. There you go. This is what we're going to do. We're going to discretize the problem, march it forward. So this is often called the method of lines. Why? Because what you do is you get your solution at this line, and then you use it to get the solution at this line of time, and then so forth, and you march forward. So everything's about these timelines that you update your solution on. Okay? And everything's now solved on a grid. Okay. So that is going to be the basic idea of what we're going to try to do to solve some generic partial differential equation, which is something that changes in time, and it's a function of u and its derivatives, so forth. Okay? What's that? T can be in there. Yep. X can be a function of x, and t and its derivatives. Okay? And by the way, really what we want to do is say that. So it's could be several fields all at the same time. And the reason I've written it this way is because if you think about it, this is already, now this is in the form of what you really want, which is, I can throw that into OD45, right? March forward in time. Here's my right-hand side. But now my right-hand side depends upon neighbors. Okay? So we're never going to get that far away from OD45 or some kind of time stepper that we start talking about in the first day of class. Okay, so I'm going to, right now, demonstrate sort of some of these concepts by solving one of the easiest equations, easiest partial differential equations that you typically would study. If you took a PDE course, you would study it within the first few weeks. Okay, this is the first one, the prototypical one. It's the heat equation. And it's just this. ut equals uxx. Okay, I'm not going to derive it, but this is a standard diffusion equation, heat equation, whatever you want to call it. There it is, and it tells you how something evolves both in time and in space. Okay? So how do we go about solving this? Now, for what we need to do is we think about where I'm going to step forward in time. So when I think about that, I've got to think about if I'm going to step forward in time, I've got to put this in a form that OD45 understands, or any kind of time stepper. Okay? So I want to change. So notice something very important. When you solve partial differential equations, your first priority is to try to figure out a way to turn your partial differential equation into differential equations. Once you get it into that form, typically in an analytics technique, you would drop it into algebra. Okay? But if you have a nonlinear equation, as long as you can make that transformation to a system of differential equations, then you just use ODE45 to solve it for you. Okay? So what we're going to do is think about, I'm going to take a domain, and my domain will be from, let's say, negative L to L, and I'm going to just chop this up into a number of points, for instance. So chop it up. That's the discretization process. You get to control how finely chopped this is. Okay? If you have a nice knife, you can just Ginsu that up. You remember the Ginsu knives? Late night TV? No? You guys too young for Ginsu? Chop through pop cans? Awesome. And it's still sharp. You can like slide through a penny and then watch this slice through tomatoes now. Okay, so same thing here. You get to slice and dice how you like. You get to pick that delta x. And how are you picking that delta x? Typically, you might want to have a certain error that you're willing to tolerate. And then you'd pick your delta x accordingly. So we're going to try to do this, and then we're going to try to solve it into the future t on this grid. Okay, so first of all, how does this partial differential equation become actually a set of differential equations? Okay, that's the first thing you want to recognize right away, is that what we ultimately want to do is get away from a partial differential equation. And the way we get away from a partial differential equation, we say, well, what do two derivatives mean? How do you calculate two derivatives? What we learned is once you chop this up, second derivative relies on neighbors. Right? So the way to think about a second derivative is to say, well, look, if I'm at the nth point, and if I want to calculate two derivatives at the nth point, I take the point in front minus twice the current point plus the point behind all over that. Right? We did this in class. This is just using simple slope formulas, right? You want to use the derivative formula, rise over run, and second derivative is you do rise over run twice. There it is. This has a certain error associated with it. But notice what it does for us. This is going to be very important. I took away space derivatives, and I replaced them with coupling to neighbors. I took a PDE, and I turned it into an ODE. Okay? That's what I just did. That's what discretization does for you. You destroy the PDE and replace it by an approximation, and the approximation connects neighbors. So in other words, if I calculate the derivative here, or second derivative here, the second derivative cares about that guy and that guy. Or girl. I don't know. It's hard to tell with dots. Okay? So there you go. That's your grid. That's how you think about then marching forward in time. So let's come back to this board over here. Look how we're working the board management today. Just back and forth. But notice here on this grid, if I wanted to go from this line of solutions, which is, let's say, at time t equals 0, and I want to advance my solution delta t into the future, then a point here in the future, what would it rely on? Well, I've got two derivatives there, so I'd have to come back to this point here, and I'd say, well, this point here somehow is going to rely on these 3 points. That's the stencil for it. These 3 points are going to somehow give me the value in the future. Okay? So we'll talk about how that happens. All right. So there's your approximation to the derivative. And so really what you have, if you take a look at that equation, then you say, well, my nth point then, the time derivative, is equal to un plus 1 minus 2 u of n plus u of n minus 1 all over delta x squared. And notice this equation holds for all n points. Right? So n is from 1, 2, 3, all the way to n plus 1. Let's say I have n plus 1 points. Now I'm going to make one other assumption here. You cannot solve a partial differential equation unless you prescribe boundary conditions. Did you like that big pause there? Was that dramatic? You know, I'm half Brazilian, and I'm all about drama. So I have a Brazilian mom, and so I learned about drama very early on in life. So I use it to my great effect in class. All right. Those are my pauses. It builds suspense in the lecture. I could tell people are getting suspenseful. Okay. So there you go. This is it. And then we have to apply boundary conditions. So let's work with what we've been working with in the code. Let's just pick some periodic boundary conditions. So I'm going to break this thing up into, this is going to be the first point, second point, third point, blah, blah, blah. This will be the nth point. This will be the n plus first point. The last point, same as the first. So my boundary conditions for periodic boundary conditions is that u of L t is equal to u of minus L t, which translates to u of 1 is equal to u of n plus 1. Yeah.
You don't need periodic, right? You can just have something for t equals 0 across the whole X domain. And it doesn't have to be periodic, right?
My initial condition?
Yeah.
No.
You
Fine.
use arbitrary thing.
Use an arbitrary initial condition, but I have to apply some kind of boundary.
Sure.
So I do this. Even though my initial condition isn't periodic, what will happen is it will evolve into a periodic boundary. Normally. Depends on what kind of equation you have. In a diffusion equation, it quickly picks up. You're enforcing now this boundary, and it starts to enforce it on the equations you get out. So everybody go with that? That's the translation. So, interestingly enough, when we start thinking about what's the second derivative here, what are its two neighbors? That one. And, well, that one is the same as this one, so really it's that. Okay? So that's how we think about that. All right. So now what we want to do is collect, then, these set of discrete equations and the boundary conditions into vector form. Okay? So we want to say, I want to write this now as the following. du dt is equal to some right-hand side f. There's no time dependence on this side, so we can just write it like here. So I just got to make a decision how I'm going to collect everything. And the obvious way to collect u would just to be say, well, how about if I just make u be the following? u1, u2, u3, all the way to u of n. Not u of n plus 1, because u of n plus 1, once I have u1, I know what u of n plus 1 is. Okay? It's the same point. There we go. There's my collection, and the question is now, what's fu? Fu is carrying this information. Okay? And what's this information? This is my second derivative. This tells me how neighbors depend upon each other. And so my claim is that for this problem, this is nothing more than this. 1 over delta x squared, that thing, times AU, where A is a matrix that conveys this information. This relationship between neighbors times U. So let's figure out what A is. What is the matrix A? So this goes back again, sort of right back to what we have already been considering in this big AX equal to B problem, right? Which is we talked about how to construct that big matrix A. So this is even a simpler version because it comes from this very simple equation. And so let's look at this. How much does at point n depend upon itself? That's your diagonal. N depends upon itself like minus 2. It sees minus 2 of itself, right? And then it sees 1 of its neighbor on the right, 1 of its neighbor on the left. Okay? So when you think about this in terms of a matrix, you see minus 2 of yourself. It's called having a negative self-image. Right. That was a really bad joke, I know. No, some people were listening. Okay. But you have a really positive image of your neighbors. Maybe it's like real life. It's like the Joneses. You know, those guys they got positive ones over there. And they in fact do. That's your matrix. Negative 2 on the diagonal. 1's on the diagonal right after. We haven't done boundary conditions yet. Okay, so that's the basic structure. You still have boundaries to incorporate. How do you incorporate boundaries? Well, you say, okay, so let's just think about it for a moment. I have -2, 1's on the neighbors. But then when I'm in this first row here, I have -2, 1's on the neighbor. What happened to that neighbor right there? Where does that neighbor live? Well, I'm supposed to have a neighbor there, but I don't, but it's periodic. So that's really like saying this guy over here is the same. So this is the neighbor. That is, U1 is equal to, sorry. Let me go back. Yeah. So U1 is equal to U of n plus 1. So U1 would talk to U2 and U0. Yeah. Getting you ready for Friday night. Did you see those dance moves? Serious? Yeah? Okay. People aren't quite appreciating this early, but I'm just throwing it out. You can watch the video later for that if you need, okay? It's just in there. It's buried. It's free. Okay. U0 is actually UN plus, it's over here, so this is the neighbors over there from UN plus 1 is, so instead of this big guy being U0, this guy's like saying, that's that guy, U of n. Yeah?
Wasn't it -1s down the diagonal? Is that different? How is that different from the question that was on the homework? Because I think on the homework, was it supposed to be negative or was it supposed to be positive?
Well, first it should be a 2, not a 1.
Oh, okay.
And so it depends on how you do this, right? So one second, let me finish this here, this thought, and then we'll come right back to your thought. Boom, boom. There's a 1. What happens down here? Neighbor, neighbor. Neighbor over here is actually neighbor over there. There's matrix A. 0's everywhere else. That's the second derivative matrix in one dimension with periodic boundary conditions. It's always how it looks like. Order delta x squared accurate. Yeah?
When they correspond to UN, though, not UN plus 1?
No, it is. That's right. So that is UN. Remember, UN plus 1 is U1. Right? So you're looking for the neighbor of U1 on that side. Well, if U1 is UN plus 1, then it's U of n. Okay? Now, back to the homework question. You should see a pattern of 1, -2, 1, and then -2. There's also the kx squared beta in here, down this thing here. Now, if I make a sign change, this could be -1, -1, 2. Hey, it was your problem. You are the boss of your problem. This is one thing we all have to understand. You are the boss of your problem. You are doling out this however you like. Okay? So if you change the sign, that's fine. But here, it's simple enough to write it in this way. And the problem, you notice that we have the two derivatives, and when you collect things, depends upon what side you want to put things on. You'll either have it a sign switch or not. Okay, so there we go. That's our derivative matrix. And in fact, then, once we have that, notice I now have my full system. du dt is equal 1 over delta x squared, AU. And then I can solve the PDE. I've turned it into a system of ODEs. This matrix A tells me how everything's connected. And then I can just use OD4.